Welcome to another exciting edition of Shader Programming. My name is Nate Nessler for Hyperactive Studios, and I will be your host tonight. So, what we have here is a layout of how the process works for the way the computer graphics are processed for rasterization. Alright, so first of all, we start out with some color vertices. In this case, we have them black, but they could be colorized. And so that's the first step when you're going through these shader processes, right? So go into the vertex shader, and it's going to be colorized vertices. Okay, and next it's going to be primitive assembly. So what does this mean? This basically is just a fancy term for saying that, hey, we're constructing our geometry here, our polygons here. In this case, a triangle strip. I like triangle strips because they're extremely efficient. I'll go over them in just 1 second. Well, I'll just talk about it right now. So the great thing about triangle strips and the reason why they're so efficient is it takes 3 points to make this one triangle here, but in order to get each additional triangle, it only takes 1 more point. So again, so now I have 2 triangles with 4 points, now I have 3 triangles with 5 points, and so on and so forth. So, you know, it becomes better and better for efficiency as you add more triangles here for computation. So anytime you can have a model converted into triangle strips and triangle fans, that's the best thing possible, because you will save so much in geometry costs. It's not even funny. It's great. It's absolutely wonderful. Also, as a side note here, the triangle strips, the quad strips and quads are not allowed on the new WebGL and on the cell phones for OpenGL ES, and so for WebGL. You have to go with triangle strips and triangle fans for this kind of stuff, or individual triangles. And the reason why this is because they have such a small space to work with on the cell phone as it is already, and you're trying to do conservation of the battery by doing a whole special scheduling system in order to reduce power usage so that, you know, it's not sucking the battery constantly, otherwise the phone will die and nothing flat. So there's a huge science and a huge thing goes into the whole battery power and management and everything, and space conservation on a cell phone. So in order to make extra room for programs and for processes and to not eat up the process of the cell phone, they took out instruction sets from OpenGL for WebGL and OpenGL WebGL, here OpenGL ES for cell phone, and in order to make the programming language smaller. And one of the things they took out was quads. But you can get the same thing pretty much with triangles. So not pretty much, you can. It's just it'd all be triangles instead of quads. So if you convert things to triangle strips and triangle fans, especially with cell phones or web, then you know you can get an efficiency here with these vertices. As an aside note, on the whole aspect with the cell phone programming, OpenGL ES at this current time, the last statistic I got was 99.9% of the cell phone industry does 3D graphics on a cell phone uses OpenGL ES. So if you are interested in going to the web, it's OpenGL pretty much as far as that goes. And the Cronus Group is doing a wonderful job with that. They're absolutely amazing. Okay, so that aside, here we go with our next step in rasterization. So now we've got our basic outline of our polygons in place for our triangles, and then we do a rasterization step, meaning that we just do a basic color fill into it. You know, and that's all there is to that. It's not much to it. It's just a basic color fill. Now this could be red or whatever it's going to be for the color. And I went actually and did go to colorizing it in the next step. And this is the interpolation, texturing, and coloring. Basically, this is all the shading techniques of your fragment shader. And remember, fragment means pixel. Well, uncomputed pixel anyways. And then we'll go ahead and load this, and bam, there it is. So there's your interpolated you know, effect across those, you know, polygons, and then you would get something like that to occur on the actual final rendering there. So very nice, and looks very good. Okay, and so that's how that process works. It goes through the different steps. So you go through the whole part of you go through your vertex shader and then into your fragment shader, and then, you know, this gets, you know, shaded from a pixel standpoint. Technically you could do this kind of gradient over the vertex shader too between vertices, but you're going to get a better result from that of the pixel shader. So again, well, you know, reason why you got the precision of a pixel versus precision of a vertex. You know, here you got little vertexes here, 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 and here. So those are pretty widely separated and far apart. Whereas, you know, the precision of a pixel shader, and the reason why you're going to get so much better results is look at the size of a pixel. I mean, like, I'm having to really zoom in on it in order to even see one. So look how small they are compared to, you know, vertex is, you know, separation between them is giant in comparison. So of course, always you're going to get a better result whenever you can do a pixel shader, but it is more costly on the actual 3D processor. So, you know, use it when you can, within reason of your requirements and what your, you know, situation allows. Let's put it that way. Okay, so probably just do that right there. That looks nice. Okay, now moving forward, and just step backwards real quick. Okay, let's look at some other stuff here. Individual triangles. This is another, okay, so now you have different drawing types. Now I talked about a triangle strip a second ago. I love them. And they're very efficient. And you can see again why you would want to do that over individual triangles. Sometimes it's not an option. You know, if you have like particle system or whatever, and you have, you could only do, you know, a set of triangle strips here with 2 triangles together, and that's it, which would be the equivalent of quad, which is what you'd have to do for a cell phone. But if you have these individual triangles like this, you have 6 points instead of just 4 points. You know what I mean? And if we had 3 triangles instead of being 5 points, you now have, yep, you got it, 9 points. So you can see how this is getting more and more expensive, and more of these individual triangles you have computed and spread across the GPU. It helps, but still, you can seriously increase the poly count for what you can handle on the GPU if you just use smart geometry creation processes in your programming. Okay, so from there, let's look at triangle fan. This is insanely efficient. Unfortunately, you can't use triangle fans for a lot of cases, but when you can, by all means, use them because they're so unbelievably efficient. Alright, so in order to get a triangle, only need 3 points, right? And then 1 point, 1 point, 1 point, 1 point, etc. for each additional triangle. That's it. So it's just extremely cheap in order to get triangles from a triangle fan. So triangle fan and triangle strips are extremely efficient and extremely cheap. Very nice. Alright, moving on, we have individual quads. Yep, they're expensive to do. You have 4 points. These are used for particle systems a lot. Makes a whole lot of sense because you have to have floating you know, image planes here flying in the air to make up the effect of fire or smoke with just a little basic texture for it. So here I have the quads as such. Quad strip. Yeah, so we have a quad here, and then each additional quad is only 2 vertices or points in order to create those. Very nice. Polygons, and these are ingons. They're referred to as polygons, but they're ingons. If it has more than 4 points, it's, you know, an ingon. So this is a 5-point ingon. This is a 6-point ingon. You can have 7 point, 8 point, 9 point, 10 point, infinite points. That's what the N stands for, is any number of points for it. These are only really good for physics. Again, you wouldn't want to have these for display purposes on screen because you could have non-coplanar polygons that have non-uniform, non-manifold geometry that's all twisted up and distorted and destroyed and won't render properly and looks absolutely terrible and horrible. It's not something you're going to want. So, you know, by having it not using ingons for rendering graphics rasterization purposes, you're best off. And then, of course, points. These are individual independent points. You can have that. That is possible also. There are some particle systems that use points, but they don't look that good. Typically, you don't have anything to work with hardly to do much with them. But yeah, I mean, you can have them. Over here we have independent lines. So here we are. They're just floating lines. These are possible too. Line loop. This lets you do an entire loop. It can be connected. It can be overlapping. It can be, you know, it doesn't have to be, you know, non-overlapping. But in this case, I did a non-overlapping one because I like it to not overlap. And here's just a line strip, and they're not going to be connected. It is just nothing more than, think of like a path, laying down like AI path or something like that. It's like a path. Okay, so there's your line strip. Okay, cool. And that's how all that stuff works. And this is for constructing geometry. And if you look through the OpenGL series, you'll see how to actually go through and construct geometry directly within OpenGL for doing like GL triangles or GL triangle strip or whatever. Okay. Now over here we have our fragment and other data. So this is where we get into our fragment or uncomputed pixels, and all the other data can come along with it. You could have depth, or just any number of things that can be used to go along with the actual fragment pixels. Okay, so pixel ownership test lets you determine that. It's a type of test. And then we have our scissor test. Okay, so a real quick explanation of the scissor test is that, well, a good way to put this is, what this does is cut out, say, you have an overlaying graphic. And just to show you an example of what I mean. Alright, so here, for instance, this graphic right here is overlaying this 3D viewport. Basically, the pixels behind this pop-up window here doesn't have to be rendered, right? Because they're being blocked, occluded by this overlaying image here, or well, actually, this could be a quad polygon here, and then have these images mapped to it, etc. So that's very cool, and it also saves us a lot of time. So, I mean, what would be the point of drawing and spending time on the processor computing the graphics behind, this image here? This pop-up 3D box, this is more just an image. You can actually select things from it. And what would be the point of that if you're never going to see it? So until it's ready to be visible, there's no point in computing it. So that's the whole point of the scissor test. It finds out, hey, is this being occluded? Does it need to be drawn or not? If no, then it shouldn't be drawn. And that's essentially what that does. There are some tricks to it, because if it's not done right, you can cause flickering on the graphics where it should be being displayed, in which because you can have it to where it's not getting updated, which is a problem. So what you can do in order to maintain that is you can copy the frame buffer to the double buffer, so that you have the same graphics across the whole thing. That's more complicated than we'll get into right now. We'll get into different buffering techniques eventually here, and how that all works in detail. But for right now, all you have to worry about here is that the scissor test basically prevents you from, keeps you from having to draw unnecessary stuff that's going to be blocked visually anyways, that you would never even see. So I mean, if this is not transparent, then it's going to be completely opaque, which means it's going to be occluded, which means we're not going to see it. It's just a whole fancy way of saying we're not going to see it. So if we're not going to see it, don't draw it. Basically, that's what the scissor test does. So this way you can have multiple floating windows or multiple whatever, and you don't draw unnecessary stuff and compute unnecessary stuff, computations. Okay, so with that, that is indeed the scissor test here. And we'll move on to the next test. And then we have our alpha test. This is for transparency. And then we have our depth test for the depth buffer. Now if you looked at one of our other videos, you would see a physical example of that and why it matters. It lets you determine whether or not something should be drawn in front of something else, for instance. It could also be used for doing focal blur. Is something going to be close to the camera or not for your focal blur? So that's important too. And then we have a stencil test or a stencil buffer. You can use this to occlude things like, for instance, if you're faking reflections in 3D by drawing a scene upside down, more or less, and then want to cut out all the other aspects other than the floor for the reflection, then you could use a stencil test in order to do that. And so that way you're not drawing the scene everywhere else, like through walls and everything, and that such thing. And basically all you do for that little trick is you make the floor semi-transparent, so it looks like you're seeing reflections. The more you make the floor transparent, the more reflective the floor appears to be. But it's just a smoke and mirrors technique, more or less. We have blending. This is very useful. It does just like it sounds. It blends. Okay, next is dithering here. And we're going to switch to Wikipedia for a good explanation of this. Here's a good example of dithering. Here's the original image. You can see the result here, and it looks nice and clean. But here they reduce the color, right? So this is dithering here. This is where this comes into play. You end up with this banding happening. As you can see, we're getting these stair-stepping of color occurring across this image here, which looks absolutely nasty. So what they try to do is go to a web-safe color palette. And this is a fixed color palette here. And so of course they lost tremendous amounts of detail. But with dithering here, and they're using Floyd Steinberg's dithering method, and I'll show you some of the, this is a great, whoever wrote this up did a great job writing this up. But basically what we're doing is we're looking at the colors available in the palette, and then we're determining what the color should be where it is placed visually here on the image. And in this way we're kind of like filling in the gaps for the color that's not there from this banding. And it gets rid of the banding, as you can see it here. So we take this image and it makes it look like this. It's amazing. So even though this color information is not there, we have this color information instead, we end up with this result because of the dithering. So the dithering is absolutely amazing. It really is. Here they've done a reduction. Now here you had your original, has a lot more pixels, right? And then they reduced it down to a 256 color optimized palette. And this is an optimized web-safe palette, not a fixed palette like the other one. And this still looks pretty good, but they're using a dithering with this, and it got rid of all that little dots. And that is a good, makes it recognizable oftentimes. When you have some dithering, you'll see these, like, it looks like these little pixelated points, and that's typical of something you would see with dithering, but still, this is far more desirable than this. You know, here, this is just terrible, this is nasty, and this is a far better solution to this, you know, by far. Here the depth is reduced down to only 16 colors. That's really not much to work with. Optimized palette in this image with no dithering. So here again, we're seeing this banding occur here, which is nasty. It's not as bad as this one here because this is really bad banding here, but it's still very noticeable. And the difference between this is a fixed palette, and then this is an optimized 16 color palette. So of course the optimized 16 color palette is going to do a better job. Now this is the optimized 16 color palette with dithering. Now you have a hard time. I mean, you can still tell, don't get me wrong, you can still definitely tell this one from this one, but this one looks far better than this image here. And then this is this optimized palette with the dithering, and you end up with some pretty nice results as far as that goes because of the dithering process. Some of the algorithms that are involved with this, we have original, threshold, random, halftone, Bayer. Bayer's ordered. Bayer's popular, by the way. Floyd Steinberg. You saw that one earlier. They were showing that one off, and this is really probably one of the best ones right here, if not the best one. Jarvis Judas and I'm probably going to mispronounce this. Nike, Stuckey, Burks, and I'm probably murdering these names. I'm not going to bother trying pronouncing that one. But you can see there's lots of different methods. Sierra, two-row Sierra, filter light, Atkinson, Hilbert, and Piano, I guess. Not sure how you pronounce that last name there. But basically you get the idea. There's a lot of different methods for handling this. Some of these are more dramatic in the look of their pointillization of the surface, but it does fill in these areas nicely. And of course you can see original to threshold with you know, you have your dithering here. This is a big improvement over this right here. Or versus random, halftone, or Bayer ordered. It's not you're not going to get very good results. So of course dithering really increases quality is what it comes down to. By filling in colors that are missing and data that's missing in the image. Of course, why would you do that? To save time, to save room in the processor, to save room in the memory, to save bandwidth for sending images across the internet, to, I mean, just all kinds of stuff. So that's why it's done. It's done for speed and efficiency in all respects. So, and it also uses up less hard drive space too. which can also be an issue if you're on a limited size capacity for a particular game requirement or something of that nature, or web or whatever. It doesn't matter. All the same scenario. Alright, so let's go on to the next one. And then we have our logic operations. If you think about if, loops, etc. Color buffer. This is the buffer that it goes to before it gets displayed pretty much on the screen. And then we get displayed on the screen. We can double buffering, triple buffering, things of this nature. You always want to at least use double buffering at a bare minimum. The reason for doing this is that if you use single buffer, you'll draw straight to the screen, and people will literally see it being drawn to the screen, so you get this nasty flickering effect occurs, and it looks absolutely horrible. The way to fix that is just to do a double buffer, and it's only like 2 extra lines of code. It's so simple to do, it's not even funny, so there's never an excuse not to do it. It's very simple, it's very easy to do, and it's something you should always do. But that's basically just rasterization pipeline, how you go through making it work for a number of things here. And if it fails at any of these processes, then of course it's going to be a problem for it to render. So then it's going to discard the fragment shader results or whatever, and of course you're going to get a problem. A good example of this, like you go to draw something on screen and the feature's not there on the 3D card, and so it simply just doesn't draw and it comes back white or something like that. That's very typical of when you have a failed process. You're going to get something like white in place of where it should be. And so instead of getting that nice anti-aliasing or nice whatever, you don't get it, or you get white where it should have been like a colored texture or lighting effect or something like that. Simply because, especially with Intel integrated, you get it all the time, let me tell you. They can't hardly do much. So it becomes a real problem and a real issue as far as that goes. So that's what happens when you have a failed process due to lack of hardware or something of that nature. But we'll go through these tests more and more into the future. Right now we're just kind of doing a cursory overview of it. Here's what it looks like. This is how the process goes. And then as we're going through these other ones, you can always refer back to these and look through the process and see what's happening. And that's particularly useful. And with that, again, my name is Nate Nessler, and thank you for watching. For Hyperactive Studios for putting this on, and enjoy the other videos.